There are other additional topics in game programming that are recurring and worth talking about. One of them is a compilation plus script way of writing games. Most of the code we talked about in other sections that isn't a scripting language, for example C++ and others, have the same general pattern. You compile it so it is interpreted to a language a machine understands, and then you run it. Compiled languages are usually very fast, but harder to develop for. When compilation becomes more complex, this process becomes lengthier. Compilation can take hours, and if we make a mistake during runtime, it could be hours or days until we realize that we made a mistake. And valuable compilation time would be lost. Instead, we use a solid foundation, usually a game engine that handles physics, graphics, and computations. A game engine isn't a compiled language, and we don't have to compile it as frequently. We then work on scripts. Scripts don't need to be compiled and work right away. A popular scripting language for games is Lua, or LUA. Lua doesn't need lengthy compilation and is also fast for the demanding game programming environments. This allows us to modify, create, and change game values and logic quicker during development. This also allows for user-made plugins, or modifications, further down the line. For example, with Lua, we could alter some rules and modify our character's health, change name, change the number of enemies, position, and other things, all without compiling. Balancing these aspects is important for enjoyable gameplay, and using scripts to produce multiple prototypes faster is a fairly common practice. The game loop is another convention for game programming. You can think of any game or application of this nature as an infinite loop. It shouldn't stop until you're instructed to do so. Every time we cycle through the loop, we do three basic things. First, we check for user input or other types of events, like timers or other sections within our code. Then, we update the underlying game state. This involves doing the math and logic behind the program, like checking for collision, moving objects in a coordinate system, and other computations. Finally, we draw the updated game state to show it to the user. And then we cycle through again. In this brief example, the player has issued a move command with the controller, which is then processed and finally displayed. Finally, we have one of the most recurring game programming topics. Collision detection is nothing more than knowing when two objects are occupying the same space and acting accordingly. Doing this in real time with the complex models we use nowadays can be quite the challenge. To detect collision, we use shapes to surround our characters that can be squares, circles, spheres, depending on the model and its complexity. These can have many names, but we can call these bounding boxes, collision boxes, or hit boxes. Notice how the box is slightly larger than our character. It stops us from bumping into a wall. Let's take this example of a 3D character. Normally, I can fly to my teammate in need of help and heal them back to full strength so they can rejoin the fight. But sometimes, an enemy can and should get in the way and stop us from helping our friend. The enemy character has a physical presence in the game to do so. This is an example of collision. It would also make sense in our somewhat realistic world that our characters couldn't walk through trees, walls, or other objects, and instead collide with them as shown here. Usually, the characters or objects we have on the screen have complex shapes. Think of a face. It has many complicated shapes and is hard to draw simply with squares. For simplicity's sake, we can represent such objects as cubes. Most 3D objects can be represented by cubes or a series of cubes, or sometimes even a sphere, depending on what we're doing. This makes checking for collision much easier. Every cycle of our program, we want to determine if any of these cubes or spheres are overlapping. That is the basis for collision detection algorithms. We can briefly think of how this would be represented numerically. If our objects are in overlapping coordinates, that means that there was a collision and we shouldn't allow the character to move further. Of course, sometimes it's not as simple, and the speed of our program or how often it checks for collisions might need to be modified. Also, the size and shape of hitboxes might need to be modified to fit the actual shape they're representing, so that the program might catch it on time or just before it actually collides. As you can see, there are many nuances to performing collision detection in real time. Collision is one of the more trickier topics in game programming and might require experience and practice to tackle, but the basics of how it works are a useful concept in both game design and 3D environments.